All right, let's dive right into this explainer. Today, we're exploring how invisible forces literally move mountains of steel, transforming the absolute chaos of a scrapyard into a precise science. We all interact with magnets all the time, right? But there is a massive leap from that tiny magnet holding a photo to your refrigerator to the industrial titans that shape our modern recycling and manufacturing worlds. Picture this. You're standing in a massive recycling factory. Right in front of you, a giant excavator with a heavy hydraulic attachment drops down onto a pile of jagged, twisted scrap metal. The operator doesn't need physical claws to grab the metal. Instead, they just flip a switch inside the cab. Instantly, tons of chaotic steel are pulled tight against the flat surface. It completely defies gravity through raw, seemingly magical power. When the machine swings over to a dump truck, the operator flips the switch again, and boom, the massive payload instantly drops. Seeing a machine just effortlessly heave thousands of pounds of metal without any moving, gripping parts, it's absolutely mesmerizing. And it naturally brings us to a really fascinating question. What exactly is going on inside that heavy machinery to create such an immense, controllable lifting force? How does a simple electrical current actually translate into this invisible, heavy lifting muscle?
So here's our blueprint for today. First, we'll look at the giants of the scrapyard, then the science of moving charge, followed by solenoids and iron cores, temporary versus permanent magnets, and finally, build your own electromagnet.
All right, Section 1, Giants of the Scrapyard.
Moving right along to Section 2, Science of Moving Charge.
Okay, so to really understand these scrapyard giants, we've got to zoom way, way in to the microscopic level. You see, anytime an electric current flows through a standard copper wire, it naturally generates its own magnetic field. You can actually visualize this invisible field right now using what physicists call the right-hand rule. Just make a right fist, point your thumb in the exact direction the electric current is flowing, and check out the natural curl of your fingers. That curl shows you the direction of the magnetic field wrapping around that wire in concentric circles. And hey, if you reverse the current, the field reverses right along with it.
Which brings us to Section 3, Solenoids and Iron Cores. Now, a single straight wire creates a circular magnetic field, sure, but it's way too weak to lift even a single paperclip, let alone a whole bundle of scrap steel. But if we take that wire and wrap it into a tightly packed coil, which is known as a solenoid, the individual fields of each turn start to overlap and interact. They combine to form this super strong, highly uniform magnetic field shooting straight through the center. It basically acts exactly like a standard bar magnet, complete with a distinct north and south pole. So here is the absolute game changer. A solenoid is strong on its own, but we can make it incredibly powerful by inserting a ferromagnetic core, think something like a simple iron bolt, right down into the center of that coil. See, inside that iron bolt are countless microscopic magnetic domains. Usually, they're pointing every which way, just completely chaotic and canceling each other out. But the second you switch on the current in that surrounding coil, the external magnetic field forces all those chaotic domains to instantly snap to attention. They align perfectly and multiply the magnet's overall power exponentially.
If you're ever looking to upgrade an electromagnet, the science gives us 4 distinct ways to pack in more power. Ready? Number 1, you can pump more electric current through the wire. Number 2, increase the number of turns in your coil. Number 3, densely pack those turns by decreasing the overall length of the coil. Or number 4, exactly what we just talked about, add that soft iron core to get those internal magnetic domains all lined up and working together.
Next up, Section 4, Temporary versus Permanent Magnets. Before we actually build our own device, we've got to answer a pretty vital question. Why doesn't a massive industrial excavator just use a giant version of the permanent magnet holding up your grocery list? Well, permanent magnets, which are usually made of steel, are stubborn. They are always on, and you can't easily demagnetize them. Imagine trying to drop a literal ton of scrap metal if the magnet absolutely refuses to let go. Electromagnets, on the other hand, use a soft iron core for temporary magnetization. Because it relies entirely on the flow of electricity, you have the ultimate control. You can adjust the strength, reverse the poles, or drop a massive payload of steel exactly where you want it just by cutting the power.
And finally, Section 5, build your own electromagnet.
All right, let's harness all this industrial science into a super practical tool. Say for picking up dropped screws in your workshop so you don't have to scramble around on the floor like a caveman. Gathering a few simple components brings the power of the scrapyard right into your hands, letting you work smarter, not harder.
You're just going to need a standard 9-volt battery and clip, a small 9-volt electromagnet that can lift around 5 kilograms, a momentary switch so the magnet is only active while you're holding down the button, some standard speaker wire, and a length of PVC pipe for the handle. You can use a 3D printed mount or even just a simple wooden dowel to attach the magnet to the pipe, plus a little epoxy to hold the whole shebang together.
Following these quick assembly steps gives you a sleek, highly functional tool. You just epoxy the mount to the end of the PVC pipe and attach your electromagnet. Run your extended wires right up through the center of the pipe to the handle. Then you solder a simple circuit, battery positive to your momentary switch, the switch down to the magnet, and the magnet back to the battery negative. And hey, here's a really fantastic bonus from our physics discussion earlier. Because electromagnets are really just coils of wire, they aren't polarity sensitive. That means you literally cannot wire the magnet backwards. Once it's wired, just epoxy your switch into place, and you've got a tool where a simple press of your index finger completes the circuit.
Now, just a quick safety reminder from our sources before you go off experimenting on your own. Coiled wires have very low electrical resistance. That means moving current can create a whole lot of heat very quickly. So, if you're building experimental coils at home, please never use flammable materials like a rolled-up tube of paper for your core. It can literally catch on fire. And for any battery-operated magnetic tool, always make sure it is disconnected when you're not actively using it. So now that you've mastered the invisible power of electromagnetism, from the extreme heavy lifting of industrial scrapyards all the way down to the elegant physics of aligning magnetic domains in a soft iron core, I want to leave you with this final thought. Take a look around your room right now. What other everyday devices in your home are secretly relying on these magnetic coils to function? Think about the speakers playing your favorite music, the motors inside your household appliances, or maybe even the classic ringing of an old-school electric doorbell. This invisible force is absolutely everywhere, just waiting for you to flip the switch.